Hello, Chemistry 11. This is Mr. Chan again. And today's lesson is going to be on Lewis dot structures. And so it's basically a continuation of your bonding notes from last day. Okay, so what I'm going to do is I'm just going to share the screen here, screen share. Okay. Now, so with the screen share, hopefully you recall what was chemical bonding. And that's that mutual attraction between electrons and protons. Now, hopefully you had a chance to watch that video, that YouTube video that I have up here, talking about the Big Bang Theory. Now, some of you might say, well, how does that relate to bonding? Well, the three guys were attracted to the ring, but they were repulsed by each other. Okay, so that's that mutual attraction and repulsion. And notice when they had to go to the bathroom, they all got up together because they had the attraction to the ring and they moved together as one to the bathroom. And that is symbolic of a chemical bond. What happens is the attraction keeps the electrons, the mutual attraction between the electrons and the nuclei keep the atoms together. Now, what I did was I talked about a non-polar covalent bond here, and I forgot to put this on, so I'm just going to put this on here. Okay, so I'm just going to stop the sharing. Okay, and I'm just going to restart it. Hopefully you folks have that in front of you. Okay, now, so what do I mean by non-polar covalent bonding? So in this case, chlorine and chlorine were exactly the same in terms of electronegativity, and the difference is 0. So if you look at the blue cloud, which represents the electrons, notice it is perfectly in the middle. Okay, it's perfectly shaded in the middle. Okay, now, what I'm going to do next is I'm going to share the next one, which is polar bond. Okay, so I'm just going to share here. Okay, so let's say if I share the screen, and let's say we share, in this case, we talk about polar bonding. What happens is hydrogen and iodine have different electronegativities. So when they share together, what happens is the majority of the electrons are closer to the iodine. So that's why we have the partial negative. Hydrogen seems to have lost its electrons, so it's partially positive. And this is what we call a dipole because there are two poles to it. Okay, now the last one I want to talk about is ionic bonding. Okay, so if we look at ionic bonding and start the zoom, here we go. If we share, let's see, where's ionic bonding? Ah, it's right here. Okay. Now, if we notice there's such a large electronegativity difference, it seems like all of the electrons are now circled around chlorine. And so what you have is you have your negative and your positive charge. Okay, so in this case, because the electronegativity is so big, one of the chlorine in this case seems to have gained the electrons, the pair of electrons, while sodium has lost it. Okay, so that would be ionic bonding. So it's just a different amount of sharing. Now, what I want to do today is I want to go over the second page of your notes. So I'm just going to screen share and I'm going to do, let me just see here. Let me just cancel something here. I want to cancel this one. I want to cancel this one. Okay. And so what I want to do is I want to screen share how we draw Lewis dot structures. Now, this one should be, again, a review of grade 10. Okay. Oh, excuse me. Now, so what are Lewis dot structures? It's used to represent the arrangement of valence electrons or outermost electrons around the atoms in a molecule. Now, the number of dots around an element symbol, so the number of dots around the element symbol represents the number of electrons in the outermost s and p orbital. Now, we're using that term s and p again, okay? Now, so in this case, for fluorine, if we look at the outermost s and p orbitals, notice that there are 7 electrons. So if we were to draw the valence electrons around fluorine, what I'm going to do is I'm going to pretend I have a little square. And what I'm going to do is in the little square, I'm going to have the electrons. I'm going to go 1, 2, 3, 4, 5, 6, 7. Notice I filled in 1 electron on each side of the square before I doubled them up. Okay, I think this goes back to off-bound principle or Pauli exclusion principle back when we did electron configuration. Now, if we take a look at phosphorus, the electron configuration here, if I were to write this out, there'd be 1s2, 2s2, 2p6, 3s2, 3p3. So notice in my valence shells, I have 5 electrons. So if I were to do phosphorus, okay, I would have 1, 2, 3, 4, 5. Now, the question is, why do we have the squares? And I'll talk about that in a few minutes. Now, the dots around the atom can be used to represent how the atoms are bonded in a molecule. To do this, we have to take into consideration the octet rule. Now, what is the octet rule? It says bonded non-metallic atoms have 8 electrons in the valence shell. Goes back to the key word is you want to have 8 electrons. Okay, this is important. Now, the only exception would be hydrogen. Hydrogen only needs 2. Okay, that would be called a duet rule for hydrogen. So how do we do this? Now, so what we do is we first start off, we arrange the atoms so that the single or fewest one is in the center and is surrounded by the others. Okay, if there's a toss-up, place the one with a higher combining capacity in the middle. Okay, I'll talk about that a little bit later on in one of our examples. Okay, so let's say, for example, we use water. So in this particular case, let's say we have hydrogen. I put oxygen in the middle, and I put hydrogen. Why do I put oxygen in the middle? Is because I only have one of them. And what I want to do is imagining if I had the box around each of these. What you want to do is you want to make sure that the boxes line up nice and neat, each side flush with each other, just like Legos, okay, if you want things nice and straight. Okay, now what you want to do is you want to count up all the valence electrons of the atom. If you deal with an ion, you add an electron if it's a negative ion, and take away electrons if it's a positive ion. So in this case, going back to our electron configuration, for hydrogen, you have 2 hydrogens, you have 1 oxygen, and it is neutral. So hydrogens have 1 electron. Oxygen has 6 valence electrons. And since it is neutral, it is 0. So in total, we have 8 electrons in total. Now, this is key. We cannot go beyond this number 8. Okay? Now, step number 3, divide the total number of electrons by 2 to get the number of pairs. So if we take 8 electrons divided by 2, what we get is we get 4 pairs. Okay? Now, use a pair of electrons to form a bond between each pair of bonded atoms. This is called shared pairs. Now, this is why I use the box. So if I go back to step number 1, where we had hydrogen, oxygen, and hydrogen, okay? And remember, we had the boxes all around. So here we have hydrogen's box. Here we have hydrogen's box. And here, where we have the oxygen box, the boxes, the ones that are side by side, what we do is we put a pair of electrons. So I'm going to put those in red, okay? And I'm going to use X's, okay? So that is 2 pairs. So these ones, the ones that I used in red in between the 2 boxes, these are what we call the shared pairs. These are what forms the bond in between hydrogen and oxygen. And these are the ones that are subjected to that tug of war. Okay? Now, it says arrange the rest of the electrons around the atoms to fulfill the octet rule, called the lone pairs. The number of shared pairs and lone pairs must equal the number of calculated in step 3. So if we were to do this, I'm going to rewrite step number 1. So we have hydrogen, oxygen, hydrogen. So we have a pair of shared pairs. Those are the ones I'm going to mark with an X. What I'm going to do is I have 2 left over because I used 2 in the shared, and that leaves me 2 left over because I have 4 in total. So now I can put up here, above and below oxygen, this is my lone pairs. Okay? Now, notice if you count the number of pairs, here they total 4. So what we have is we have 2 shared, so that's 1, 2, and we have 2 lones, 3, 4. That matches up the total that we have in step number 3. Now, you might say, well, Mr. Chan, how did you know that you wanted to put the lone pairs around oxygen? Because remember, we need the octet rule. So if I were to put an imaginary circle around oxygen, what we have is we have 8 electrons around oxygen. Remember, hydrogen, we only need 2. So if we were to draw a circle around hydrogen, notice we have 2 electrons here, and here we have 2 electrons. Okay, so that's how we fulfill the Lewis dot structures. Now, step number 6 says if you cannot fulfill the ideal, try 2 shared pairs or 3 shared pairs. In this particular case, because we finished off in step number 5, right now this one is not needed right now. Okay? But don't worry, we will get to it. Now, So what I want to do is I want to go over a couple of examples right now. So on your second page, okay, I'm just going to split it in half. Okay. So let's say, for example, I have something like, oh, I don't know. Let's do NH4 plus 1. Okay. Now, what we're going to do is we're going to do the first 3 steps. Okay. The first 3 steps was arranging, counting up the number of electrons, and to find my total number of pairs. Okay. Now, so if we look at NH4, what I will do is I will put N in the middle. And if I put a square around it, I will put, let me put hydrogen as a different color. Hydrogen on this side. Hydrogen on this side. Again, the sides of the squares need to be flush with each other. In other words, be nicely set up. Okay. Now, that's step number 1. Step number 2, remember we have our valence electrons. So if we have 1 times nitrogen, we have 4 times hydrogen. And because it's a positive, okay, why is it a positive? Because it has a +1 charge right here. So what we have is 1 times 5. We have 4 times 1. Here we minus 1 electron. Okay, why? Because remember, in step number 3, if you go back to the video, if you have a positive ion, we take away an electron. Okay, so in this case, what we have, one thing nice is that I can make this nice and big. In total, we have 8 electrons. Okay, total is equal to 8. And the number of pairs is 4. Okay. All right. Now, again, what do we do? So this is steps 1, 2, 3. So if I do this, this is steps 1, 2, and 3. Here is step number 4 and 5. So in this case, if I were to draw the hydrogen, nitrogen, hydrogen, 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 remember first is the shared pairs, which I will use as x's. So we have 1, 2, 3, 4. Okay. Now, in this case, we're done. We don't have to do step 5. Why? Because if we look at the number of pairs we have, that's 1, 2, 3, 4. That's the 4 here. And if we were to take a look, if we drew a circle around hydrogen, there is 2 for hydrogen, 2 around this hydrogen, 2 around this hydrogen, and 2 around this hydrogen. Yay! And if we look at nitrogen, there is 8 around this nitrogen. Yay! So we're done, except for one thing. Because this is NH4 plus 1, we have to indicate that it's an ion. So what I need to do is I need to put a square brackets and put a +1. So in this case, if we put a star, we need to put brackets around ion. Okay, something for you to be aware of. All right, now you might say, Mr. Chan, that's pretty easy. Challenge me. Okay. Now, sorry, my daughter is just video chatting right now, so that's okay. Now, what we're going to do is I want to do CO2. Okay, let's try CO2. So we have CO2. Now, if we do steps 1, 2, 3, okay, it should look something like this. O, I'm just doing it real quick. C, O. Okay, I'm just doing it really quickly here. So you have 2 times carbon, 1 times oxygen. It is neutral. So what you have is 2 times 4, 2 times 6, 0. So what you have is, oh, no, 2 times 6, 1 times 6. And what you get is 8. So you get, let me see, 2 times 4 is 8. Oxygen is 2, 4, 6. Carbon is 2, 4. Oh, no, wait a minute. Whoa. This is what happens when I go too fast. So you have 2 oxygens, 1 carbon. There you go. Ah, there you go. So you 12, you have 16 electrons total. And you get 8 pairs. Okay, remember, 8 pairs. All right. Now let's build it. So that's steps 1, 2, and 3. Now, if we do steps number 4 and 5, you will notice you have a problem. Okay, so we go like this: oxygen, carbon, oxygen. We use 2 pairs, so 1, 2, 3, 4. And then the other, you're left with 6. So we go 1, 2, 3, 4, 1, 2, 3, 1, 2, 3. Now, if we look, we have 8 pairs because we have 2 shared, 1, 2, and we have 1, 2, 3, 4, 5, 6. We have 8 pairs, but notice, are there 8 electrons around all of them? Now, this oxygen is okay. This oxygen is okay. But notice, carbon is sad. It only has 4. Now, no matter what you do, you cannot fulfill an octet if you stop at step number 5. So what you need to do now for this one is you actually have to go to step 6. Step number 6. What is step 6? It says, if you cannot fulfill the ideal with 1 shared pair, try 2 shared pairs or 3 shared pairs. Okay, so let's try, in this case, if I'm going to step here, you might say here, can't do. So let's do step 6. So what we're going to do first of all is we have O, C, O, like what we've done before. But now we have 2 shared pairs. But let's add them on one at a time. So here I'm just going to get this oxygen out to give me a little bit more space. So let's do here, we still do 1, just like what we had done before, but now let's add another 1 to this side. So what we have, and then we do the rest. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. Okay, notice we still have 8. If you count all the little dots and X's, we still have 8 pairs. But notice we're not having an octet. We still don't have an octet. So again, if we take a look here, we have 8 around oxygen here. We have 8 around here. And then we also have 6 around this carbon. We're getting closer. Now, some of you might say, oh, Mr. Chan, let's do a triple bond. Let's do 3 shared pairs. But before we do that, let's max out all the double bonds first. Okay, so this one, it still doesn't work. Still no work. So let's try 2 shared pairs. Okay, so let's go here. Again, oxygen, carbon, oxygen. Let's do this. So we have 1 shared pair on either side. Let's double up on either side. And now we go, 1, 2, 3, 4. Doesn't matter where I put the lone pairs on the oxygen? No. But if we were to check, notice there's 8 electrons around this oxygen. We have 8 electrons around this oxygen. And notice for this carbon, we have 8 electrons. Yay. Okay. So in this case, we had to do a double bond on both sides of the carbon to make sure it works. Now, notice I'm doing it 1 step at a time. I did the first one first, checked that. Then I did the second one. Okay, so when you're adding double bonds, don't go crazy on the double bonds. Don't put double bonds everywhere. We start with 1 at a time. All right, it's like eating a donut. You don't stuff your face with 5, 6, 7, 8, 9, 10 donuts all at once. You start off with 1 at a time. Okay, so if we've maxed out the double bonds and it doesn't work, then we try triple bonds. Okay, it's a progress. Now, some of you might say, well, Mr. Chan, how come we see in books carbon dioxide looking like this? What do the lines represent? Well, the lines represent 1 shared pair. So if you have a single line, that represents 1 shared pair. Okay, 1 shared pair. And this is called a single bond. 2 lines means 2 shared pairs. 2 shared pairs. Okay, I'm just going to use the official words here. Pairs. That would be a double bond. Here would be 3 shared pairs. That would be called a triple bond. Okay, now there is a special type of bond. Okay, so we have a single bond is 1 line, double bond would be 2 lines, triple bond would be 3 lines. This one would be James Bond. Ha 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 ha. Okay. Okay, just for you to be aware of. All right, so this is a little bit of review of grade 10 material. Okay, and so hopefully you folks, this should be a little bit of a review. Now, what I'm going to ask you to do is for homework, I'm going to ask you to do the odd letters. So A, C, E, G, I, K, M. Okay. I want you to try those out for fun. Okay. Be careful about G. Okay. Just for you to be aware of. Okay. So I want you to try that out, just a few for fun. All right. And what I will do is I will also go over this one here. Okay. I will go over H as well as a special one. All right. So if you want to try it out, great. If not, don't worry about it. But I will give you the answers to A, C, G, I, K, and M next day. All right, folks. Thank you very much. All right. Hope you have a good day. And if you have any questions, feel free to email me, okay, before if you have any questions. All right. Thank you very much. Have a good day.